In this video, we're going to learn about rational functions. So, rational function is actually a quotient of polynomial functions where the denominator is not the zero polynomial. And because we consider quotient, so we have to care about the domain of rational function because this is not the set of all real numbers, but it is a set of real numbers for which the denominator is not zero. So for instance, the domain of fx equals x plus 3 over x plus 1 is actually all real numbers that are not minus 1. And the domain of g of x, which is x minus 2 times x plus 3 over x minus 2 times x plus 1, is actually the set of all real numbers that is different from minus 1 or 2, because in this case the denominator is the product of x minus 2 and x plus 1. Okay, so in order for the denominator to be non-zero, then x must be different from 2 and minus 1. So in these examples, you might notice that g of x actually looks a little bit like f of x, because if we see that the numerator and the denominator of g of x both contain a factor of x minus 2. But the point here is that because when x is equal to, then x minus 2 becomes 0. So actually we cannot cancel out the factor x minus 2 from g of x to get f of x. And obviously you can remark that the domain of fx and g of x are actually different. So for this reason, fx and g of x are actually different rational functions. So keep in mind about that. Now, a polynomial function f of x can be thought of as a rational function by identifying fx with fx over 1. Okay, and as we mentioned before, from time to time you can have rational function where the denominator and the numerator contain the same factors. So for example, in f of x, you have x squared plus 1, x minus 3, and x plus 1 as common factors between the numerator and the denominator. So in order to remove the redundant factors from the formula of f of x, you can get the lowest term form of a rational function. But as I explained before, if you simply remove all the redundant factor by cancelling them out, then you might lose track of the domain of the rational function. So if you want to keep the rational function correct, then besides writing the lowest term form, you need to keep track of the condition for which the denominator is different from 0. So for example here, in this case, if you write fx in lowest term form, then you already get rid of the factor x squared plus 1 and x minus 3 from the denominator, right? But because x squared plus 1 is always positive, then you have nothing to keep track of. However, for x minus 3, then when x is equal to 3, then x minus 3 is 0. So in order to make the lower terms form correct, then you have to add the condition that x is different from 3. So from this lowest term form, you can actually understand that the actual form of the rational function should have some factor of x minus 3 on the denominator. Okay, that is how you can have the simplest form of a rational function without losing the actual domain of it. Now we talk about asymptote of functions. An asymptote of a function or a graph of the function is actually a line that the graph of the function goes nearer and nearer, closer and closer to the line, but do not cross that line. So for example, in this case, if you consider the rational function x squared over x squared plus 1, then as x go to minus infinity or x go to plus infinity, then the graph of f actually will get closer and closer to the line without touching or crossing it. Okay, so in this case, the line y equal 1 is called the horizontal asymptote of the function x squared over x squared plus 1. And if we generalize this example, we have the notion of horizontal asymptote of a function, meaning that the line y equal a is called a horizontal asymptote of a function f(x) if whenever x tend to minus or plus infinity, then the value of f(x) approach a. The second kind of asymptote is a vertical asymptote. A line x equals c is called a vertical asymptote of a function g of x. If the value of f(x) approaches either minus infinity or plus infinity whenever x approaches c, meaning that the graph of f(x) is closer and closer to the line y x equals c without touching or crossing it. So in this example, f(x) is equal to x cubed over 8 times x minus 1. So for x equal 1, when x get closer and closer to 1, then the value of f(x) goes either to minus infinity or plus infinity, depending whether x approaches the line x equal 1 on the left or on the right. This can be easily explained by saying that if x approach the line, the vertical line x equal 1 from the left, meaning that x get closer and closer to 1, but always less than 1, then the difference x minus 1 is always negative, right? While x is positive. So the quotient get closer and closer to minus infinity. Whereas if x approach 1 but from the right, meaning that x minus 1 is always positive, then as x gets close to 1, the factor x minus 1 gets closer and closer to 0, but always stay positive. So for that reason, f(x) will get closer and closer to plus infinity. The last type of an asymptote is called oblique or slant asymptote, meaning that it is a line that is not vertical nor horizontal. And the same definition applies. The line y equal ax plus b, where is called an oblique asymptote if the graph of h of x stay close to the line when x go to infinity. So for example, the line y equal x is actually an oblique asymptote of the function f(x) equal x cubed over x squared plus 1. Now we come to a specific type of function that we talked about in the introduction to rational functions. So actually rational functions, very often they have asymptote. So the following are a list of conditions for a rational function to have asymptote. So first, if in the denominator of the rational function we have factors of the form x minus alpha, but the denominators contain more factors of this than the denominator, then f(x) will actually have a vertical asymptote as x equal alpha. So for example, if the rational function is x minus 1 times x plus 3 over x minus 1 power 3, then the denominator have more factor of x minus 1 than the denominator. meaning that this function will have a vertical asymptote at x equal 1. And similarly here in this rational functions, so the denominator has x minus 3 and x plus 1, and they both have more of these factors than the denominator has. So this rational function have two vertical asymptotes at x equal 3 and x equal minus 1. The second condition is that if the degree of p of x of the numerator is less than or equal to the degree of the denominator, then the rational function f(x) will actually have a horizontal asymptote at y equal a to b, where b is the leading coefficient of q of x, and a is the coefficient of x power n of p of x, where n is actually the degree of the denominator. So in case the denominator and the numerator have the same degree, then actually a is the leading coefficient of the numerator. But when the degree of the numerator is strictly less than the degree of the denominator, then then a is actually 0. So for example, in this case, the numerator is 2x squared and the denominator is 3 times x squared plus 1. They both have degree 2. So the horizontal asymptote of this rational function is actually y equal 2 over 3. Whereas in this example, the denominator is of degree 1, whereas the denominator has degree 2. So the horizontal asymptote in this case is actually y equal 0. Now the last criterion is that if the degree of the denominator is actually 1 more than the degree of the denominator, then f(x) will have an oblique asymptote. And we can determine the oblique asymptote by actually computing the quotient in the division of px by q of x. Actually, in this case, because of the degree restriction condition, then Sx is actually of degree 1, and it is actually the oblique asymptote of f of x. So, for example, if you want to find the oblique asymptote of the rational function f of x depicted in the slide, then you have to take the Euclidean division of the numerator for the denominator. And so first, if you want to find the first term in the quotient, then you have to divide the highest term of the numerator by the highest term of the denominator, then you get 10 of x, right? And then you multiply 10 of x with the denominator, then you get this line, and taking the difference between these two lines, you get another polynomials. Then taking the highest coefficient of this one and divided by taking the highest terms of this one divided by the highest term of the denominator, you get the second term of the quotient. Okay, so you do the same trick again, and after that you will get here the remainder of the division. It is already of degree 2 less than 3 here. So you know that this is actually the quotient, and this is actually the remainder, right? So for that reason, the asymptote, the oblique one of f(x) is actually y equal 10x minus 13. Okay, so that is an example to illustrate how we can find the oblique asymptote of a rational function whenever the degree of the denominator is 1 less than the degree of the numerator. Okay. Now we talk about wholes of rational functions. So, in case where in the quotient expression of rational functions, whenever the numerator have the same or more factors of x minus alpha than the denominator, then actually the graph of LS will have a hole at the point with coordinate alpha and g of alpha, where actually g is the lowest term form of f of x. Okay. So, for example, in this rational function, we have a factor of 2x minus 5 appearing in both numerator and denominator, and they both have one factor of these on the numerator and the denominator. So it means that we will have a hole here at the point where we can compute the y coordinate using the lowest term form of g of f of x, which is actually 3 times x plus 1 over x minus 2 in this case. So now we can compute the coordinate of the whole of f of x, which is 5 over 2 and 17 in this way. Now we come to analyze the graph of rational functions. So in many cases, we do not have the explicit formula of a rational function, but instead we are given its graph. So how can we analyze the graph and say something about the formula of the rational functions? Well, actually we can say a little bit about the formula of a rational function given the graph of it. So for example, in this case, we are given a graph of a rational function fx equals gx over hx. So we try to identify gx and hx from the data that we have here. So first of all, we know that the x-intercept of this graph is actually the origin. So the x-intercept is 0, right? Meaning that we should have a factor of x in the denominator of f of x. And because through the point, through the origin, the graph actually crosses the x-axis, meaning that the multiplicity of x should be odd. Okay. And moreover, we have 3 vertical asymptotes, x equal minus 1, x equal 1, and x equals 3. Then here, let's take a look at the first asymptote, x equal minus 1. We see that the way the graph approach the vertical line x equal minus 1 is that actually they approach x equal minus 1 in different direction depending on whether x approach minus 1 on the left or on the right. It means that fx should have a factor of x plus 1 with multiplicity, with odd multiplicity. Okay. The odd multiplicity actually determine the way the graph approach the vertical asymptote. And here, the same here for x equal 1. So actually, when x approach 1 on the left, then the graph will decrease to minus infinity, and when x approach 1 on the right, and the graph will increase to infinity. It means that the multiplicity of 1 here in this case is also odd. However, for x equal 3, you see that whenever x approach 1 on the left or on the right, the graph both go up. So it means that the factor of x minus 3, the denominator of f of x should have a multiplicity even. Okay, so from these, we actually get a lot of information about which factor should appear on the denominators or denominator of the rational functions. And one more thing that we can say is that this graph does have a horizontal asymptote y equals 0. It means that the degree of denominator is strictly less than the degree of the denominator. and because of that, we do not have any oblique asymptote of the function. Okay, so these are information we can get from the graph of the functions. So by now, you should be able to analyze this given graph and tell whether it is actually the graph of the function 3 times x squared plus 1 times the square of 2x minus 5 over x minus 2 square times 2 times of x minus 5. So you just need to pause the video for a little bit while and try to analyze the graph and to show whether the graph is actually this corresponding graph of the given rational functions. So I hope you enjoyed the video.